All right, in this video, we're going to try another example of a Lewis structure. We're going to try the structure for the sulfate ion. Recall that the sulfate ion is SO4 minus 2. So we're going to calculate our total number of valence electrons here, 6 for sulfur and then 6 for each oxygen. So that's 6 times 4, 24 plus 6, so 30. But then don't forget we have the negative 2, so 32 valence electrons to place. And so we'll choose sulfur as our central atom, and we'll start connecting the oxygens in around the sulfur with single bonds, so like this, like this, like this, like this. And that means we placed 8 electrons total, so that's minus 8. That's 24 electrons left to place, and we can place them around our oxygens first to satisfy their octets. Like that. And so that looks like everything's happy. And we placed 24 electrons overall, so minus 24. That's 0. Everything has a nice stable octet, and we can put our charge over here of minus 2. So this is one possible structure. Let's call this structure number 1. Now, remember we discussed that you can have more than 8 valence electrons around sulfur. We can have an expanded octet. So we could make a double bond from, let's say, any one of our oxygens. Let's do this one here. So we'll make a double bond from there. We'll just throw the bonds in there, and we'll get another structure, another possible structure here. So, or we can get S double bond O, single bond, single bond, single bond. Put all your dots where they belong. Like that, like this, and then you get this possible structure here, because remember sulfur can have an expanded octet. So now we're kind of deciding what's the best structure: sulfur satisfied, sulfur more than satisfied, or remember we saw in the previous example that sulfur basically has room for 12 electrons for bonding because of the half fill. Some of the p's over here being half filled in terms of the orbitals, and then the completely empty 3D sublevel. So sulfur could have up to 12 electrons in the bonds there. So what we could do is we could just grab another one and make another double bond. Doesn't really matter which one. Let's just select the one over here and then put that into the bond. And so another possible choice is this here. And don't forget to put your brackets with your charge. So these are some choices that we can have: choice 1, choice 2, and choice 3. Now, we need to decide which one's the best. Now, some students might say, why can't you make more double bonds? Theoretically, you could make more double bonds. We'll see why we won't in just a bit, but really sulfur in its expanded state could really have up to 12 valence electrons, and that's about it, just because of the fact that it's in row 3, and that's all it can basically have in the valence electron area. It already has its other areas full. So let's just deal with these structures right now. We can have satisfied, a little bit more than satisfied, and then more than a little bit more satisfied. We'll calculate formal charges to see which is the best structure here. So we'll start with the green area. And remember from what we saw earlier, all these oxygens essentially look the same. So we just have to calculate it once and apply it to all the oxygens there. Just make sure they're actually connected the same way and have the same features on them. But we have 6 valence electrons minus 6 dots minus 1 line. That's negative 1. And so all of these would also be negative 1, negative 1, negative 1. And then sulfur, on the other hand, this is 6 minus 4 lines minus 0 dots, is positive 2. And this makes sense because overall our molecule charge is -2. So if you add all these up, +1 minus 4, that's -2. But notice that we have a lot of formal charges everywhere. So, I mean, if our other molecules are a similar spread, that might be tough to decide, but let's see if our other molecules are a little bit better. So all these single bonded oxygens here, they're all -1 formal charge, as we saw from our previous calculations. And then a double bonded oxygen, that's a little bit better. That's going to be 6 minus 4 dots minus 2 lines. That's 0. So 0 formal charge there. So we have a little bit less formal charge spread out here. And then our sulfur, on the other hand, is going to be, so 6 minus 1, 2, 3, 4, 5. Minus 5 lines minus 0 dots is +1. So we have a +1 over here. And that still adds up to -2, but we still have quite a bit of spread. It's less spread than the... it's smaller non-zero charges compared to the first structure, but still there's a lot of non-zero charges there. Let's see if the next one is a little bit better. But right away, I just know that I'm probably not going to use structure number 1, just because it's worse than structure number 2. And then structure number 3 over here, if I do that, I can get, so double bonded O is 0 here, 0 here. This is -1. This is -1. And then my sulfur is 6 minus 6 lines minus 0 dots is 0. So yes, there's still some formal charge there. I have no choice because the overall molecule is -2. This should add up to -2. But notice that there's a lot less formal charge on all the atoms. It's only on 2 atoms now instead of being on 3 atoms like in choice 2. So, in 4 atoms like in choice 2. So choice 2 would not be the best choice. So the best option would be option 3. So therefore, number 3 is the best choice in this particular scenario for sulfate. And then what you might notice is you could also draw some resonance structures now from structure 3. So ignore structure 1 and 2; those are out of the way now. And from structure 3, we could do some resonance structures. So we could. I'm just going to do structure 3 here. We'll do a resonance arrow. You can draw the same sort of molecule, but instead your double bonds maybe over here and over here. So we shifted double bonds over a little bit. And so we get these as resonance. With a -2. And then you could continue the resonance by shifting them some more. So you can maybe get like that, like this, and then -2 over here. And then there's probably other resonance structures you can do. So perhaps you can have a case where you have your double bonds up here. And down here. So as you can see, there's several contributing structures to sulfate. We have possible structure like this one over here. We shifted it over this way. We shifted it up here. Now we have it this way. We could possibly do one more like this, where they're across from each other this way. And then the single bonds are up here. And then -2 as well. And I believe at this point, we covered all the possible resonance structures that exist. So we have 1, 2, 3, 4, 5 contributing resonance structures for sulfate. But again, it's all based on structure 3, not on structures 2 and 1. Maybe they contribute in some way, but they're not equivalent, significant resonance structures just because they don't have the best formal charges. You'll notice here, if you calculate all the formal charges, it's the same spread, right? You're going to have, for example, -1 and -1, and then 0, 0, and 0. Same thing here. You'll have -1, -1, but then 0, 0, 0. So it's the same relative spread throughout the molecule, which makes them all equivalent contributing resonance structures. And the overall structure of this is going to be a resonance hybrid. In the next video, we're going to take a look at the preferred Lewis structure for H2SO4. In other words, there might be more than one option, and we're going to have to figure out which one's the preferred one based on the formal charges.